Thank you for being here. My name is Wilfried, and I am working at OVHcloud, which is a France-based cloud provider. At OVH, I'm an engineering manager for both databases and observability. And among other things, I am part of the Grafana Champions community, which means I know a little bit about observability. The mission of my team at OVHcloud is to provide an internal databases service for the whole company. So we are not addressing customer, we are addressing our product team so that they can build their product, control plane, data plane, without caring about their databases. To do so, we are building an infrastructure which needs to scale and to be resilient so that the product, our customer product, are reliable at all time. And lastly, as DBA for the company, we need to foster SQL skill at the company level. So when I talk about infrastructure, here is a high-level view of what our infrastructure looks like. We have clients, which is most of the time hosted on Kubernetes, but sometimes this is VMs, bare metal, whatever. Those client application connects to our cluster through a load balancing. This load balancing exposes two ports, one for the write traffic and the other one for the read-only traffic. And according to probes, we are able to route the traffic to the correct instances in the cluster. When I say cluster, I'm talking about at least a 3-node cluster with a primary node, which is responsible for the write traffic. It can also handle the read traffic. And obviously, the read-only traffic is only select. We have a third node, which is dedicated to backups that we can stop at any time we like to take snapshot of the file system and archive this snapshot to make our backup. This is the example for our Postgres cluster, but we have the same architecture for our MySQL cluster. With that being said, we have a lot of questions from our coworker about why their databases are slow, their queries are slow. And back in the day when I started at OVHcloud 7 years ago, we weren't able to answer those questions on the spot. So let's say we have the head of the public cloud asking why our control plane is slow. We were to spend a lot of time SSH something, tailing logs, and so on to give them the answer. And obviously, the first part we are missing is a good observability on the whole database perimeter. I'll talk to you about our cluster. In fact, I missed something. We have more than 100 clusters running in production today. This means a lot of servers. And what we did, this is actually what I did 3 months after joining OVH. With time, we have switched backends, but the general idea is the same. We have taken all the logs from Postgres and MySQL, parsed them, and stored them in an efficient way and structured way in our OpenSearch cluster. We have done the same things for the metrics. We have the system metrics, database metrics, load balancing metrics. Both data stores are used through Grafana. We have built efficient dashboard. Due to the size of our perimeter, we have a lot of logs and metrics. The numbers are here, but this might be significant to store. Hopefully, you can do the same with managed services. On my end, we have a skilled team that provide us both the Mimir backend and the OpenSearch backend. So the amount of data is not the issue here. The real question is how we use and leverage those data. So we all love dashboards. So on the left, you can see the system metrics. On the right, you can see the amount of transaction per cluster, and we have a lot more of dashboard. Those ones are metric-based, those ones are log-based, and we can see the amount of slow query per cluster, per databases, per application, the error rate, and so on. And with that, we can drill down really easily to understand and find where a new behavior happened on the cluster. With our first-class observability, we then understand that our hardware were undersized. This means that the hardware was not capable enough to sustain the workload. One of the top products of OVH are bare metal server. We have a lot of them, different size, different performances, and what we have done is vertical scaling, all nodes of all clusters everywhere. So this is the figures. The first line is the starting point, and the last line is where we are today. For some cases, we have even bigger cluster than that, but this is not the majority of our cluster. And what we try to do is to maximize the performance we can gain from every aspect. So faster and more cores, bigger RAMs, bigger disk, faster network, in an attempt to improve the quality of service from a user perspective. But even with the top-notch hardware, we were still witnessing a lot of inefficient workloads. Because we have all the logs that we need, we were able to say how many slow query, and someone want to guess what is behind the stars? Maybe? Anyone? In 2 seconds, I will show you the answer, and you will be shocked. So basically, what we witnessed is that for a single database, and we have a lot of database now, we were witnessing 2 million slow query for a single database in a week. I don't know if you have a sense of the scale, but this is really a lot. So with the observability and the logs, what I enjoy to do is every Monday, first thing in the morning, pull all the logs, all the scores of each database, and write a nice mail to the whole company to say database A is the slowest of the whole company for the last week. And I engage with each team regularly to raise their awareness and get the slow query fixed. When I say slow query, at that time, a slow query where every query that was more than 1 second to run on the cluster. So what we did, we set the threshold, everything above, we try to fix it. And when we reach a point when there is not enough query to fix, we lower the threshold and repeat the same process again and again. Today, we are at 250 milliseconds to say a query is slow. While trying to fix the workload, we have also identified that some queries were optimal, but the data model, the structure, the schema of the database was not. And it was not efficient nor optimal because the developers were not skilled enough in SQL. So the challenge we try to fix is to catch and prevent slow query before they reach the pre-production. So this is tricky because you have to fix something that doesn't exist on your observability radar. And what we did was to design a new workflow to modify a database schema. So the developer will design a feature called something, then publish its code. It will go through a peer review, then a database engineer review, and then it will be deployed in production. This was time-consuming because we have something about 20 to 30 new modifications every day. So this is time-consuming. And what we did is we automate the process with our CI/CD to identify the bad practice in the schema. So not enough indexing, too much indexing, not the right type of data, and so on. And with that, we are able to keep up with the new modification every day and raise awareness progressively, because the CI will fail, and then the developer will have the instant feedback that is not doing something optimal. And after that many years of work, for all our 1,200 databases and counting, we are under 1 million slow query, for everything. So if you remember, at the beginning, we were at 2 million for a single database, and now for 1,000 database, we are under 1 million. And voila, everything know how to write an efficient SQL query. We have top observability, top of the laser-curve data model, and so on. But I have still 12 minutes to tell you about my life. So my team was not really happy with me, because there is a lot of things to do, to raise awareness, to share knowledge, to improve the resiliency of the infrastructure, do the server upgrade, the OS upgrade, the database upgrade, and so on. There is too many things to do at too many places. So we have to change our approach. And because this is SREday today, we try to use the SLO framework. So basically, the SLO framework, which is you have to define an objective and an indicator and an agreement and so on. We try to apply it to our databases, and the trick is to understand that a database is just like any other API, HTTP, gRPC, and so on. This is the same approach. Instead of a get, you do a select. Instead of a post, you do an insert, and so on. So we have to define the objective, find and design the synthetic monitoring agent, understand how the Prometheus histogram work to extract meaningful information to simplify our life. So as a user of a database services, your expectations are what? You are able to connect to your database, pull data, and write data. And hopefully you can do that fastly enough so that your customer are not waiting too long. So this is exactly what we have done. You have the real queries that we are using to monitor our infrastructure. So for the availability, we take the total amount of failures divided by the total amount of requests, and we have a ratio, an error ratio, which is used to compute how far we are from the target. So basically, we can say that we want 99.99% of the request or opening connection and so on succeed. For the latency, this is a little bit more complex, because we want to know how fast we can open a new connection or write or read data. And thanks to the Prometheus histogram, so this is not yet the native histogram, but in Prometheus, histograms are cumulative. We have to define the bucket of our histogram, and then we can sum the amount of requests below or equal a threshold and divide it by the total amount of requests. And then we have our second indicator that can be broken down for how fast I can open a connection, read data, and write data. The last thing we missed was a synthetic monitoring agent. For that, we have patched what is called SQL with a couple of flavors of it on GitHub. We are using the fork from Just Watch, which we have patched to expose the execution time of each query. And after that, this is the same process that you are already using on Kubernetes. We have the Prometheus, which is scraping our metrics and storing it. With that, we have in the first line the availability, the total of the success rate or the error rate, and then we have the latency in percentile. And one thing really interesting, if you look at the first panel in the second row, which is something like that, there is two distinct groups. Do we have anyone who want to guess what are those two groups? No one? Okay. So the first one below is how fast can I open a new connection on a MySQL cluster? And the second group is how fast can I open a connection on a PostgreSQL cluster? So when your DBA says that you have to pull your connection or put connection pooling software, they are right, because opening a connection on a PostgreSQL cluster is costly, and you have the proof right before you. With this nice monitoring, we had our first win just a couple of weeks after putting it in production. The graph here shows a fiber channel failure in the data center. So everything was working, just a little bit slower. Without this whole process, we will not be able to detect the impact of the loss of one single fiber channel in the whole data center. There is something that you want to be aware of is how to aggregate all of those information. What is the quality of service of a single cluster when you have multiple indicators? We have availability indicators and we have latency indicators broken down, open connection, read and write with multiple percentile. How to aggregate this information to show your user the real quality of service of their cluster. What we have chosen is to have a really strict aggregation. For each cluster, there is 7, and at each time, we take the worst one to bubble up this information. You have the cluster, we have several clusters within the same region, so the quality of service of a cluster is by slice of 1 hour, the worst error budget of each indicators. So we have the error budget of our whole clusters, and to have the quality of service and error budget for a region, we take the worst by a 1 hour slice of all the clusters, and so on and so on and so on. We are not done yet. This is my team working on the database while I am in conference, and we want to engage more with our stakeholders to adjust the target and the threshold. We want to have also the right focus at the right moment for the right cluster. And this is why we will apply a multi-tiering this approach. So we will have the standard silver, bronze, and gold for the criticity of the clusters. And for some cases, rare cases, we will introduce the vibranium, because I cannot find a better name, this level, which is for the clusters, the database, which needs everything custom, from the hardware, the training, and the SLOs. And finally, because I have talked about a lot about relational databases, we will add the same approach for the key value and the columnar stores that we are also providing. And this is it for me. And I can take the questions 4 minutes earlier than the quota. Thank you.
Questions?
Thank you for the presentation. I have 2 questions. The first question is, you were showing a slide where you were detecting slow schemas and like bad model design in your CI/CD pipeline. Can you talk about more? Powered by CDS.
CDS is our internal continuous integration and deployment software. This is basically GitHub Actions.
Okay, but how do you automatically check whether there is a missing index from the code?
Okay, so our user have to declare their schema in a versioned model, and each time they submit a pull request, we trigger the continuous automation and look at the diffs and check if there is the bad patterns that we call it, and we try to identify that you are creating a field probably that time without a time zone. And this raises an error and your build will fail. Or probably you are referencing a foreign key without indexing it. And this will cause slow query. So we try to catch it. We have two phases during this pipeline. There is the one that we call offline. This is basically 20 grabs on your diff, and what we call online. So we apply your schema in an empty database, and we do some queries in it to look for patterns. And with that, we can fail your build if you miss something.
Got it. Thank you. And the first question, maybe real quick, regarding the general database architecture, you were showing that you're load balancing and redirecting queries to read-only queries to the read-only instances. Are you doing this on the HTTP level based on the method? If it's a get method?
No, this is at the TCP level.
TCP, okay.
Each application can connect to either the read-write TCP port or read-only port, and based on the port which the application connects to, we can redirect the traffic to the correct node of the cluster.
Yeah, it's really fascinating presentation. My question is, what tools do you use to, supposedly from SLO side, you notice some slow queries? How do you actually drill down to the slow query for each individual team? Is that down to them to drill down in production, or you'll be responsible for looking to the slow queries?
Okay, so...
And also, what tools do you use for this?
We only use Grafana for that. Your logs are stored in an Elasticsearch backend, correctly indexed and parsed. We can just say, show me all the logs of the database SREday. So we have all the logs related to this database, and on that we can just filter and show the queries that are above the threshold.
Oh, so yeah, I suppose on Elasticsearch you can search like some duration, execution duration longer than certain.
Actually, this is done at Postgres or MySQL level, and we ask Postgres to log only queries that are below the threshold. So we know for a fact that every query that are in the logs are slow, based to our threshold.
Oh, okay. Interesting. Thank you.